Okay. Now, are you done or just are you still working on it?
Still working.
Still working. Okay, no problem. And in the meantime, I'm just gonna write that on my whiteboard that what is gonna happen and but I assume that it's these kind of concepts by now it seems much easier. We have done enough exercises. Okay, I have this one. That's what we know. That's gonna be a company's profit. Okay, and now also we know that the x also we have x's here, which they are representing, I should say. The cost of one ticket. Okay, and now imagine for the first part, we say that if okay, now what else do we need? Okay, guys, are you ready now that we just started together? That ready, guys?
Yes.
Then in case if you have missed anything, I should say you can, I should say as long as I move to, I should say to solve this one, you can also uh, complete your answer. Okay, the first part that we have here on the y-axis, we know that the y-axis represents what? It represents our P of X, which is going to be the total profit, which is a function of the X, which is the cost for a ticket. Okay, now I'm just going to just go to plot it. I just go to the Desmos to do the plotting, and also you can, let me share my screen with you on Desmos. Okay, let's go to the Desmos. That's what we use that for. I should say do some of the graphics of the course. It was -6. We had P of X, which is a profit. It's equals to minus. Guys, can you please someone just read that equation for me? Minus 60x squared plus 118, huh? 1800x plus 16500. Okay, it seems that the plot, guys, look at that. Do you see the Desmos, which I have shared that with you? You zoom it out, you see?
Yes.
It's, I should say, you see that we have at the peak of, I should say, our plot is going to be at 15, which represents the x, and 3000, it is going to be, I should say, you see, that's the peak of the plot. We are just going to get to that to see how do we get that one. And also, we come here to see that the plot is coming all the way down there. The plot is a polynomial, but however, you see, that's the thing which is the x-axis has an intercept with. You see that, this point? It's around 37. The y-axis is going to be 0. Guys, everybody sees that right now?
Yes.
Yeah? You see that? When we have that, I should say, the polynomial plotted in the Desmos, we see that it has two, I should say, 2 points, which they have, I should say, the y-axis, which is 0. Give me a second. I'm just going to grab one piece of paper to denote these numbers for myself, that when I just go to my whiteboard, I do not have to come back to these points. And you see, apparently, there is another point. You see these 2 points, guys? The y-axis for all of these 2 points is 0. You see that? These 2 points, the y-axis is 0, but the x-axis, one of them occurs at the point which is approximate to 37, and the other one happens when the x is equal to -7. And we also saw the peak of our plot. Guys, any questions about the plot that we just did that on the Desmos? Everyone is fine with it?
Yeah.
Yes? Okay. If everyone is fine, I'm just going to go back to share, I should say, my whiteboard. And in order to do the whiteboard, I'm just going to do, I should say, a plot which is not going to be on a scale because of these values that you see here. I have some crazy values. You see this one, 16,500. Oh, I'm not on whiteboard anymore. You see that this one is crazy. 16,500 is too much. This slope is 1,800. It's too big. Then the plot which I'm going to do is not going to be on a scale. However, I'm just going to, the thing which I'm going to do, I'm just going to do something for demonstration. I saw that there are 2 points which the plot is going to be 0 at the x-axis. I know one of them is going to be, for example, here. For example, one of the points that we intersect the x-axis is going to be this. But also, before we continue further with that, I'm just going to show that to you, any points that we have. For example, let's imagine A is the point which belongs to this plot. We say that we show the point like this. If I just want to use that an array, I show the point like this. The first part of the point represents the x, which it is the cost of one ticket, and the p of x represents, I should say, this one, which we have here. It's the company's profit. It means that if I just want to show any points, the first item, the first element represents the x, the other one represents the p. Then we saw that there are 2 points with the x. If the first one, it was supposed to be 37, The P of X is going to be 0. Also, I just want not to make you confused. I just want to say that this one equals to this. I can show that like that, X and P of X. That's what do I have. I have two method to represent any points, any arbitrary points on my graph. Either we call that a column matrix, or we show that by a pair. And the first unit, the first point, which has an intersect with, I should say, with the y, with the x, is 37 tickets, which it means that it's gonna get, I should say, 0 profit. That's interesting to interpret it. And also the other one was -7 and 0. And also we saw that we have a point which is a little bit abnormal. That point was here. And here, let's say, imagine here, if we assume that the x is gonna be 15, there is a maximum point, as that's the reason I said that I'm not gonna put that on the scale, because we assume that this point on our y-axis, which is a profit, it's 30,000, and the x is 15. At this point, we assume that the maximum happens, and the plot is gonna be represented like that. Then if I just wanna plot my function, not with the scale, it's gonna be something like this. This point is a point that we said that this one is gonna be the point that there is some irregularity, something happens. It seems that something is happening there. You see that? It's at the very top, it's the very height. And that's essentially the plotting of these things. Before we move on, we have to just interpret the things which happen there. The first of all, you will see that we have some parts of the plot that we have, for example, it happens that we intersect the x-axis at one point, which that one point is what? Is -7. Look at this. This point, which is -7, it seems that the profit is going to be 0. But do you think that this point should exist? That the x is -7? These points should not exist, because as we interpreted the x represented what? The cost of one ticket. For example, you want to go to a movie theater, you want to watch a movie, the cost which you have to pay for one ticket, maybe it's going to be $20. You are not going to pay -$20. You see that? The cost of a ticket, it has to be a positive number. Then as a result, this point, which represents the cost of a ticket, should be minus. It doesn't make sense, because this point does not exist. We do not have a cost of a ticket, should be 0. And it's going to be valid for anything on the left side of the origin of our plot. Then it means that when you are doing your plot, these points of your plot, which I'm just going to zigzagging it, they are not valid for your graph. I can show that this to you also in a way that I show that these points, which I have cross on it, it means that they have negative value for their, I should say, for their x. And as x represents the cost for one ticket, and the cost cannot be 0, cannot be negative, these two parts are not valid. Then the plot is valid from the right side of the x-axis. The plot is valid to this right. But also we have one more point, that at the cost of a ticket of 37, when you sell 37 tickets, your profit is gonna be 0. You see that point? It is strange that when you sell 37 tickets, the profit is gonna be 0. When you do the business, sometimes they call that point break-even point. Then they had to just put the value positive here, which the model maybe is not the model that it should be very interesting, not many realistic. These points, if you are interested to talk about the business, normally they call that these points break-even point. Break-even point. This is the point that you sell a minimum number of the tickets that your, I should say, the cost and the profit becomes zero. Then after that, you can grow and accumulate more profits. But in that case, the profit, it seems that it's going to be zero then. Then that we are not going to talk about this part, because you see that below this part, which is, I should say, our intersect, it's, you see that the profit, it goes below the zero, which it means that the profit which you have, the P of X, is going to be less or equal than zero, equal to zero at this point, but the rest of it is going to be less than zero then. It means that you are making loss. If you sell more tickets, you are making loss. And that's why we do not go into much realistic interpretation of this model in the book, because it doesn't make sense that when you sell more tickets, you are making loss. But nonetheless, we focus our attention to the part of the question that we want to solve. Any questions, guys, so far?
No.
But guys, remember, for your quizzes and for your exam, remember the first part which I do some kind of a problem exploration. I plot, I show the value of the intercepts, and also I show that, for example, at the same time, I try to interpret the numbers, the intersects, the slopes, and those kind of stuff. That's the thing which you have to do also. You have to do that on your exam. If you miss these first parts and you just jump in to just solve the question, you do not get the full mark. Remember, this part is crucial. And also, we have one point here, which it seems that we are selling zero ticket, but we are making some money. We have some profits. I'm gonna go back to the Desmos again to show that point to you. Not this one, this is gonna be, I wanna share the Desmos. Okay, let's go to here. Okay, nonetheless, it's not going to be easy to find it on the Desmos because the values are so drastically too high. We can find this point, even ourselves, that we see that, okay, what is going to be this point, guys? This point that we have an intersects with the PX axis. What is that point? Anybody can say, you get a prize if you say that point. What is this point?
0.1.
Zero on the X?
Yes, X is 0. Y is 16,500.
Fantastic, that's correct, because that's going to be our intercept. That's going to be our intercepts on, let's say, on the x-axis. You see that? On the y-axis, which is going to be our p-axis, which is the profit that we are making. You see that even though if you do not sell any tickets, you sell zero tickets, still you are making some profits, which we have to ask the management of that company, what kind of a model you have in your business that even though if you sell zero tickets, you still are making profits. It depends on the thing which they do. Maybe they sell ice cream in the theater, and even if they do not sell the tickets for the theater, they make this profit because of, I should say, selling the ice cream. And that's going to be the value of our intercepts, which is always, guys, remember in your exam to interpret the definition of your intercepts. Then what does it mean if the x goes to 0? What value you get on the y? And what does it mean? Okay. So far, all the things that we have done was to explore what is a problem and what is it's trying to tell us. And now we have a good understanding of the things which happens in the business, in that movie theater, and about the tickets price and the total profit. But before I move on to do the next part, I'm just going to teach you something which is going to be relevant also for the course which we are going to focus today. We touched that on that topic also yesterday, but right now here we are just going to focusing on this point. You see, I'm going to focus on this point, and I'm just going to call that point, let's say, x sub-index m and p of sub-index m. Later, you see why I call this m. At this point, you see that what happens there. At this point, you see that the profit which we have, when we are selling the tickets, we start to sell the tickets, the cost of the tickets is going to be between $0. Before we reach to this critical point, which is 15, you see when I move towards just 15, I move in that plot like that. It seems that the profit is going to get higher, 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 getting bigger, 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 goes to this point. You see that? But after I reach the point 15, I'm moving to the point 37 before that I'm on the point 15 to go to point 37. You see that the profit is getting lower, and it seems a little bit strange. It's very interesting at the same time that we reach to a point, that point is 15. Before that, we see the price, the profit is increasing. You are getting richer and richer and richer. But as soon as you get to this point, to this very top point, the behavior changes. You are not in luck anymore. You are getting poorer and poorer. You see that how it's a disaster. It's a disastrous point, I call it. Because before you reach to this point, you are getting rich. As soon as you are getting to this point, your profit is going down and you are getting poor. Do you like this point, Laura?
Yes.
Huh? That's the good point. Yes, Jasper, Anki, and Sylvia. That's an
Yes.
Yes, Sylvia.
Yes.
That's right, Jasper and Anki. You see, this point is very interesting because when we know this point, we should not be troubled. You know, we do not have a trauma that, okay, what happens, we can plan for it. We see that we can forecast. We see that as soon as, for example, imagine that you are getting to an investment. When you know that at this point, which is 15, when you can plan and when you can predict, when you can forecast that when you get to the point 15, you are making money from your bank. But as soon as you get from the point 15, you are gonna lose your money. Then what is a plan, Jasper, at that point? You withdraw your money from the bank, before you get to the 15, or as soon as you are to the 15, because you know that after 15 you are losing money. That's right. Then why to bother to lose your money? Then you withdraw your money. Then you see that these points are very critical to understand them. These points are very critical to predict them, because you can always make some strategies in the business, at least, that before you get to this point that you're gonna get poor and you lose your money, you withdraw your money, you change your investment, because at that point it seems that the function behaves suddenly different. Everyone is okay with this concept? Yes?
Yes.
Awesome. And now, guys, how to get, the question is this, and essentially that's going to be your new lesson for today, and we're going to spend the rest of the day about this problem. How to get, we finish this one, then we just go for a break. Then the problem here is that we just want to find a strategy, a method in the math In order to find the points like this, that sometimes it becomes a kind of a point, I call that point of a trouble. I call that point of a trouble because, you know, the behavior is not going to be, the behavior changes. Sometimes you are, at this case, you are making money, but after that you are losing money. Then it's crucial to find a point before you lose your money. And now the lesson that we just started right now is in order to find the value for X. The value which we have for this one here, that the time that you are start to lose the money is 15. But we got that value how? I got that value from plotting on the Desmos, which is not always reliable. You do not have always Desmos. The function which you want to plot is not always easy to plot it. Then we are looking for an analytical method to find the point that the function suddenly changes its behavior. For example, imagine the function it's people's behavior. For example, imagine you can represent your mood as a function. This point becomes for you when you are laughing. After that point, you start to cry. And when you are looking for this point is a time before you start to cry. Or when you are crying, you suddenly start to laugh. This point is the point just before you start to laugh. Now we just want to find these points there. For our case which we have here, in order to find this, we have a method. We say that in order to find, we say that it's going to be step number 1. Let's call this point. Step 1. Step number 1 is going to define the analytical spontaneous rate of change of your model. It's going to be our step number 1, which is going to be our step number 1. In order to do that, we have done so many similar things for these problems. Let me get the color here. Okay. I want to find the spontaneous rate of change. We have seen that, I should say, since 5 days ago, that spontaneous rate of change, we can call this A, which our spontaneous rate of change has 2 interpretations. We are going to focus on that with this interesting part today. The analytical one, we saw that the spontaneous rate of change, it's essentially this mathematics interpretation, representation, that we say that, okay, we come here to write it in this way. We say that it's going to be the D of, and also D. I'm going to change the color, and I write that P of X with respect to the X. Correct? Guys, remember this? We talked about that yesterday. We saw that this is a kind of a notation. So far, we haven't done any math. The first part, which I have drawn, which dpx over dx is a mathematical notation which signifies the spontaneous rate of change. Which, if you want to calculate this, it changes to this formula, which we did that before. Which it changes to this, becomes, as you remember that, becomes P of, oh, that's bad, becomes P of X plus H, which is gonna be, oh, sorry, not H. Sometimes I mistake the notations from different books. P of X plus delta X, minus P of x divided by delta x, which we saw that in that case, we push delta x goes to 0, and at the same time, you get to know this part next year. We put a sign as LIM, we call that limit. We do not focus on that part, what does it mean, but we know that how to find this presentation. We see that we go to our model, which is going to be P of x here. Wherever we see x, we replace it with x plus delta x. Then we subtract it from P of x itself. Then we simplify some terms which are going to vanish. Then we factor delta x and remove delta x from denominator with the one which is factorized at the numerator. Then we push delta x to 0 wherever we see delta x, we put it 0, then we simplify the terms. If you do this, which I'm sure you can do that because that's the thing which we did many times before. If you do this, you get to this simplified format. You get to minus 120x plus 1800. When you go to your calculus class next year, you see that there is a very easy shortcut that you do not essentially need to do this formula. You can just in 1 second, like me, which I did, to get this formula. But at this stage that you have to practice this grand formula. We call that grand formula. You have to follow this one in order to get this. Then you see that the rate of change which I drove here is gonna be this. Any questions, guys, so far?
No.
No, everyone is fine. Laura, Jasper, Sylvia, Anki, everyone is doing great?
Yes.
Yes.
Okay. If everyone is doing great, I'm just gonna move on to the next page and continue from there because we are gonna do step number 2. Okay. Okay, I'm gonna go to next page number 2, and from here, I'm just gonna rewrite the things which I did. I saw that the spontaneous rate of change, I'm gonna rewrite it. I pulled that EIS, which is gonna be spontaneous rate of change, was what? Was minus 120x plus 1800. This is our spontaneous rate of change. You see that we have also, besides from, I should say, the physical interpretation, you know that, for example, you can, for example, you can come here before I just go to step number 2, because guys, we have done so far step number 1. Step number 1 was that to find the analytical spontaneous rate of change, and that's the thing which we have done. We are right now done with step number 1. Step number 1 is finished. But I'm just going to do something before we move on. I say that, for example, we know that if, for example, in spontaneous rate of change for x equal to 0 is going to be how much? Nobody knows?
1080.
You mean 1800, huh? You put the x equal to 0, then you get 0 times minus 120 becomes 0, then you get only 1800. Correct?
Yes.
That's right. We have a geometric interpretation. Which we learned it yesterday. This is what? It is the slope of a tangent line at point x equal to 0. I just wanted to just make a quick review of the thing. We talked about that yesterday. It was just a review. It was just a review. This one is a review. Review from yesterday. That's what we call that, the geometric interpretation. Okay. Now, we are going to go to the second step because what is our plan yet? We need 5 minutes, then we go for the break. The plan, as I said, the plan is that to identify this point, the point that it makes, I should say, the behavior of the function suddenly different. For example, it's sunny now, it becomes rainy immediately. The minute that the weather changes from broad sunny into rainy, it's that point. For example, we have a different example as you see. Okay, the step number two in our process to find that point is that find the 0 points of the model which is derived for instantaneous rate of change. It's going to be our step number two. And I'm just with the blue, I should say letter there. I'm just going to put it there. Then that's going to be the task. Step number two. Step number two is this, that I have to come here to equate the thing which I did. It means that whatever I drive for instantaneous rate of change, which was, I put it equal, which is d of p of x over d of x, I equate it to 0. Then I solve that equation. And that's what do I mean, the 0 points. You see this here on the description, 0 points. It means that you equate this equation equal to 0, then you solve it. That's what do I mean. It means like what? That's the process. My instantaneous rate of change equation is this, correct? Then I put minus 120x plus 1800 equals to 0. And that's very interesting because that's the thing which we are talking about in the second step. Equate the spontaneous rate of change equal to 0. Then the thing which I'm going to do is this. I come here and I put how to solve this one. It's the easiest thing which we know. I put this one to the other side. I get that 120x equals to 1800. That's an easy thing to do. I take minus 120x to the other side of the equation. When it becomes plus, then I have 1800 where it is, which is the plus sign. Then I get what? The result. X should be equal to 1800. I divide both signs by the thing which I have, by this, and I'm going to find it. How much is that going to be then? Guys, please answer. How much is that going to be? 1800 divided by 120.
30.
How much?
50. Oh no.
How much? Guys, how much? How much did he get? 15? Right.
Yes.
Yeah. Sorry, what?
Oh no, I mean is 15 the answers.
Oh, 15, huh?
Yes.
Fantastic. That's right. 1800 divided by 120, it's 15. Thank you very much. And now, guys, I'm going to go back. Remember this point, guys. I'm just going to put a heart next to that. I'm going to put all with the heart. I love it. I love these points. Why do I love it? Because if I go back to my plot, the point that I was interested to see that the function changed its behavior from making profit, then suddenly change its behavior to making loss and lose money. I got it from the plot, from the Desmos was 15. You see that? You see this 15, which I put heart next to it? Guys, everyone
Yes.
sees that?
Yes.
Then everyone, look at this. If you do not even have a Desmos, that you cannot plot it, because checking with these points with the Desmos is for someone who doesn't know the math at all, who does not know how to just, what is a function, how to work with the function. But now that you are doing the advanced functions, now you do not know even the functions, you're working with the advanced function. Then as a result, you have to be able to find these kind of points with these two steps. Step number one, find the instantaneous rate of change. Then step number two, solve that equation as an instantaneous rate of change and find the roots or the 0 points or the roots. And that point is gonna be the point that the function changes its behavior suddenly so dramatically. Okay. This point is what? This point is on the x-axis, correct? I'm going to go to step number 3. Step number 3, guys, is going to be what? Show the full representation of the, I call that critical point that you found. However, the critical point is going to be what? The roots or 0 points of the spontaneous rate of change. Guys, I changed the font. I think that font is better, huh? It's bigger. Look at this. We are now at the step number 3. It's going to be the final step. Then we go for the break. For step number 3, we see that, okay, in order to do step number 3, we do this. For step number 3, we said that we are looking for the critical points. Guys, this point that we draw, it's 15, which it shows that we call that critical point. What is a critical point? The critical point essentially is a point that the roots of your spontaneous rate of change and makes the spontaneous rate of change 0. And that's the x that we drove. We call that critical point. For step number 3, we say that to show the full representation of the critical point that you found. It means that full representation. It means that you have a critical point. Let me change the color. It means that you have a critical point and you called it x naught. Okay? Now let's pull that xc. I put C. C stands for critical. For example, in our case, how much is our xc? It's 15, huh? Then you come here, the full representation is this. We call this point, I call that point C, which is a full representation. It becomes either xc and p of x in our case. Otherwise, you put c, which means the function, which represents, I should say, the general function. Or it's equal to this one, x and p of x, which I'm going to put that as a critical. Okay, and now go back to the thing which we did. What are our critical points from the example, guys? xc was how much? 15, right? That's what we got it from here, 15. The full representation, what was p of x? The p of x was minus 60 x squared plus 1800 x plus 1615, correct?
Yes.
That was our initial model that we started with. Then now, if I just want to find what is going to be of p x of c, it means that p of 15, and I plug it in there. Well, how much is that going to be? It becomes minus 60 times 15 to the power 2 plus 1800 times 15 plus 1650. And you get what? P of 15 becomes how much? If you use your calculator, I think it's gonna get to 3000, which we can call that dollars because it represents the dollars. Right?
Yes.
Everyone is fine?
Yes.
Thanks. Sylvia, Anki, Jasper, Laura. Any questions so far?
Nope.
Great.
Nope.
Then essentially we are done because we are able to say that the critical point that we were looking for, if we call that C, it's gonna be this point, 15 and 3000. That's essentially what we saw that on the Desmos. We saw that it's gonna be 15, and we saw that it's gonna be 1300. You see this point here and 15 there. And it seems that we are so happy now because we are able to talk about this point. Now, to wrap up, we just learned these points. Step number 1, find the analytical form of spontaneous rate of change. Step number 2, find the 0 points or the roots of the mathematical format of the spontaneous rate of change. Step number 3, find the full representation of your critical points. It means that you plug your x of c, which is the roots of your spontaneous rate of change, into the full equation. Then we are done. Now we are able to find the critical point, which is going to be the point that the function behaves drastically. look at this one, for our case, was the fact that you were making the profit, things were so nice, you were so rich, but when you got to that point, the critical point, you lost your money. This is the interpretation of this example. For example, it's going to be the point that, for example, you are happy. When you get to that point, you become so sad. You see, there are contrast effect. Sad and happy. Crying, weeping. Sunny, rainy. Making money, losing money. Do you get the interpretation of that point? Yes, everyone?
Yes.
If yes, anybody has a question?
No.
No. If you have no questions, please enjoy your break for, I should say, 15 minutes. Come back by 10:10. Then we continue with the class then. Okay?
Okay.
Awesome. Guys, see you then in 15 minutes. Please be back by 10:10. See you guys later then in
See you.
15 minutes. Okay, now let's come back to continue and finish the course before we just go to the second break. Then from the third break, we either do the lab for the modeling, which we just want to do with the R, or we finish the whole course, we do the whole thing tomorrow then. Tomorrow is going to be, I think it's going to be Thursday, right? Okay, now, okay, we'll just go back there. I'm still going to continue at this point with the exercise which we did. Everyone, you see all of you see the whiteboard, huh?
Yes.
Awesome. Guys, look at this point that we just got it before we just go for the break. What we did before was, I should say, this point, that the point was essentially a point that the instantaneous rate of change of our model at that particular point, which we drive to be 15, was 0. And at step number 3, we were able to find the full representation of this critical point. But guys, look at this. Imagine that if you, for example, this is the price, the profit for the business, or you can think of it to you yourself that, for example, it's going to be the maximum return of your investment if you save your money with one of the banks in Toronto. You see that when you start from the X, which is going to be X is going to be from 0, then when you move on towards, I should say, this point, you see that when you move on, you are increasing your profit. You are gradually building on the money which you have. You're getting rich gradually. You're getting richer, 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 richer. You make that much money. It becomes the maximum money which you earned from either selling your tickets or have an investment in your bank. This point is the maximum money which you get. Then you start to get, for example, lose your money, lose your money, lose your money, lose your money. You go here, and if you do not do anything, you become poor. You get broke. This point. You see that? And now this point that we said that you get to the maximum point, it serves us as a point that we call that point the maximum point. And that's what we do that, let's say in, let me pick up a good color. The good color, which, okay, look at this one. This point, I show that by a straight line parallel to the x-axis, and I call that max. Then you see that they have a maximum here. They have a maximum here. Then I'm just going to go to the next page, and I say that we get a critical point. The critical point that we get, we got, let's say, we call that critical point, we call that P of C, for example, which it was represented by this column matrix that the x was supposed to be 15, and the p of xc, which is the critical point, was, we just got that to be 30,000. We can fuck off of $30,000 in the case that we just drawing it from there. But the thing is that we call this number based on the plot that we saw. On the plot that we saw here, this point, this critical point, served to be a maximum point. You see that? I wrote here maximum. It's maximum point. That's what we can infer from just looking at the plot itself. When we look at the plot and we see that, okay, that's going to be the plot, and okay, it's going to be, for example, you are getting increase in our investment, then we just start to decrease it, then it's going to be the maximum point which we get. It's from the plot itself. But we do not want to always just rely on the plot. Then now we are looking for, let's say, we are looking for a case that, I should say, our model should be independent from, I should say, our plots. We do not need to use the plots anymore. In order to do that, I'm just going to come here and draw a graph. It's going to be this. And now okay, let's get this color. Our XC critical point is 15 at this point. Okay. And now I'm just gonna, before I move on, I'm just gonna go ahead and also draw something here. And here I'm just gonna write the function itself. What was, I should say, my instantaneous rate of change? The equation. The instantaneous rate of change equation which we drove was what? Was, I think, minus, it was this one, minus 120x plus 1800. And we say that, okay, this axis which I have on the top, guys, please listen to the way which I'm just going to analyze, I should say, this problem, because it's crucial. You are going to rely on these kind of methods in order to find, we call that the local minimum or local maxima. That's a crucial thing that we are going to do. We are doing it right now. Then please listen very attentively. I call that this is going to be my x-axis. And apparently it's going to be the thing which we decided, that x equals to 15 is going to be this line. And I assume that this point, it's going to be x equal to, let's say, equal to 0. The line represents x equal to 0. Okay, now, guys, if this one, which I have here, it's the instantaneous rate of change which we have. Let me double check to make sure that that's the correct one. 1800 at the back, that's the correct one. Look at this one here. What happens if I just put x equal 15 inside this plot, inside this equation, which is my instantaneous rate of change? Guys, listen to this one. What happens if I plot x equal 15 inside this equation, the instantaneous rate of change? How much do you get? You get 0, huh? Because this critical point, you remember from step number 2, that this critical point is essentially a root, a 0 point for this one. then it means that if that's going to be the root, if you plug it in there, you get 0 for it. Does it make sense to everyone? Then that's how I'm just going to show that to you like that. This is going to be my 0. I put it on this vertical line, which I have there. Okay. And now, what happens on the x-axis? What happens if I put some number before between x equal to 0 and x equal to 15, which it shows the extent of this interval, x between 0 to x equal to, let's say, 15. I'm just going to pick up a random number, completely random, and I call that random number, let's say, 10. If that random number is going to be 10, if I plug it into the instantaneous rate of change, I say that INSS for x equal to 10, how much do I get? I get minus 120 times 10 plus 1800. How much is that?
600.
That's so true. Thanks, Anna. It's going to be 600 plus, correct? Which we see that this 1600 is something positive. It's not negative, it's not 0, it's positive. Then because this is positive, I just come here and I just put, it's a random thing between these ones. It means that in this interval, which is between x0, which it was the thing that you were allowed to find it in your domain, until 15, which is a critical point. You always put your critical point there. If you put any random number between this, it gives the full picture of what's going to happen in this interval, which is x between 0 to 15. With an example that if x equal to 10, we got the positive number, which it means that this interval, it's positive. But guys, before we continue, we just move on again to our geometric interpretation of this sign, which is the sign of our instantaneous rate of change. Why it is positive? What does it mean? It means that if I go back to this plot, for any points which has x equal to 0, which is there, to x equal 15, which is here, not the 15 itself, because at 15, the intercept, the instantaneous rate has become 0. Any point between 0 to 15, if the sign is positive, it means that the slope of the tangent line is positive. It means that it's somehow between parallel to, let's say, for example, the quadrant 1 and 3, it's always in this direction. It means that the slope is positive. Then it means that when you got positive, it means that the function, the slope of a tangent line is positive. It means that this is in this direction. Now, I go back again to the same pictures which we have. Then we say that, okay, now, I should say in that model, we saw that our physical interpretation was that the x should be less than 37, because the 37, that was the point that we saw that. We said that we only take the x, which belongs to these intercepts from 0 to 37, based on the interpretation that we had. Then I come here, I say I pick up any number, x, which is between, let's say, let me pick up this one. And I call this one x equals to 37. And I say that I'm going to pick up another number which extends in this interval between x equal to 5 and x equal to 37. I'm going to pick up a number. What number is the easiest one to pick up and put it there? Let's think that I just get the number which is going to be 20. I say that the instantaneous rate of my function, when x is equal to 20, 20 is a random number which I selected between 15 and 37. Then it means it becomes how much? Between 15 to 37. If I put 20, how much do I get inside the function? I get minus 120 times 20 plus 1800, which is essentially equals to minus 240 plus 1800, which is essentially how much? Minus 600. And look at this one. This minus 600, which I got here, is less than 0. Then we see that for a typical number, for a random number, which stands from 15 to 37, I get what? I get a number, I get a result which is negative, which this one represents the full behavior and the nature of my numbers in this interval, which it means that it's going to be negative. And also, remember these parts, we are not going to bother ourselves with these parts because these parts, they are beyond our scope and our domain. And now we come to a very interesting point. We come to a very interesting point. And the interesting point is that the conclusion. Guys, listen to this very carefully. When you have this plot, which also it means that the negative intercept, the negative slope also, the geometric representation means that from here to here, from x15 to x37, the slope of a tangent line for any points along this interval is negative. It means this, which it means that when you are in this scenario, that you have a critical point, x15, and you have a jump from the positive to the negative, these points that you have here, it acts as what? As a maximum point, which essentially you see that your x, which was a critical point, after our analysis, it's inferred to be the x as the maximum. Right? And that's the thing, that's the lesson that we just get from here. And I just put that, I should say, put the heart, lots of heart here. It means that that's the thing which we love it. And how we decided on this? Because of this rule. Because of this rule. When we change from the plus to minus, the point, your critical point is a maximum point. However, if the case was different, Any questions, guys, so far?
No.
Laura, Sylvia, Anki, and Jasper, any questions?
No.
Everyone is fine?
No.
Okay.
Yeah.
Now, we just move on to the next scenario. We say that, okay, imagine that our instantaneous rate of change, which we had it over here as, let's say, minus 120x plus 1800, we change the sign. It means that, for example, we come here and write, for example, as a different scenario, we said that, imagine that our mathematical model is going to be this. I'm just going to change that one very quickly. Then I say that, okay. I say that, okay, the profit which we're going to have, it's going to be a different scenario. I say that it's going to be now plus 60x squared minus 1800x plus 1650. Okay. And now imagine that this is somehow different from the thing that we did, I should say, a couple of almost an hour ago. In the previous example that we started from the book, we had this sign minus and we had this sign positive. This one is a little bit different. And we think of it as, I should say, a new model that we just want to, I should say, to investigate and analyze it. This one is going to be our new model. Okay, this one is going to be our new model then. Okay, now I'm just wondering quickly, just give me 1 second, drink some water to drink. Okay, the first thing which we do is that we initially want to plot this function. I'm just going to go to share my Desmos with you. I'm just going to go back to the same function which we had, but I'm just going to make some modifications only with these two first lines. Okay, and you will see the plot. I'm zooming the plot to show that to you. Guys, you see this? Oh, I didn't share my, did I? No, I didn't share my, oh, sorry. I didn't share my Desmos. Sorry. That's my Desmos, and that's the function. Only the changes which I made for minus 60x squared, which I had previously, I change it to the plus, and for 1800, I change it to the minus. And I'm just going to zoom the plot. You will see that. That's going to be around this point, which is now 15,300. The function we have, I should say, a kind of hole inside the function. It's 15,300. And when you see that, the function goes all the way up there, and it doesn't have any intercepts. It goes all the way to, it should have an intercept, which is going to be, I should say, it goes to 16, 1500. It intercepts, I should say, the y-axis, which is going to be the p-axis. Okay. Now I'm just going to go back to my whiteboard. And I'm going to show that to you. Let me show the function like this. And I say that this one is going to be the point 15. And it goes all the way up there. I put this one like that it shows that the plot is moving all the way up there. Okay, and this point is going to be 3000. Function moves up like that, and the function moves like that, and the point which intersects, you see, it's going to be 16, 15. Okay, now we are ready to just move on. Look at this one, guys. For this one, we have this scenario. I only changed these ones, and we just want to follow the same thing which we did. But beforehand, you see that at point equal to 15, you have this point on the plot, which shows that the coordinates of 3000 on your profits, and also you will see that intercepts. This is going to be our intercepts, which it means that, okay, with 0 tickets, you still make that much money. That's going to be the definition of the intercepts that we have had. Okay. And now I just want to just jump in right to those 3 steps which we had. I'm just going to again review that with you. The first step that we talked was that to find what? The spontaneous rate of change. I say that, okay, here is going to be step 1. Step number 1 was that to find the instantaneous rate of change. I say that the instantaneous rate of change is what? If you just follow this formula that we talked about that. Look at this one, this formula, this one, the master formula, the grand formula for the spontaneous rate of change. You can come here to find it. I'm just going to go ahead to write the end formula, which is going to be 120x minus 1800. It's the instantaneous rate of change. For the second step, I say step number 2. For step number 2, I equate this equation goes to 0. I say A instantaneous should go to 0, which you end with this. You get that 120x equals to 1800. Then you end up with the x to be how much? 15. That's exactly the same value which we derived on the previous scenario. And now I'm going to go to step number 3. Step number 3 is that to find the full, I should say, representation of this critical point, because you remember that we call this one critical point, because critical point are the roots of the equation which you get at step number 2 when you solve this equation. For step number 3, I'm just going to come here to do what? To come here to say that I'm just going to plug, I should say, the value of x15 inside the equation. Then I get what is going to be the p of 15, which it means that it's going to be 16 times 15 squared minus 1800 times 15 plus 1615, which it gets to equal to what? 3,000. Then based on step number 3, we are able to find the full coordinates, I should say, of our critical point. The critical point, which is going to be here, I call that critical point, because this point is the root of the instantaneous rate of change equation. We say that the full representation, x of c, it's essentially this. X is 15, y is 3,000. Okay, but now we have one more step to do, and that's going to be this step, which I'm going to follow that again. And we do that, I should say, based on, I should say, our charts. I wish if I had some space here. No, there is no space. Okay, I'm just going to do this one here, and I'm going to write these charts. For the first one is going to be the root, and this one I'm just going to draw it to just write the equation. And you see, this one represents our x-axis. This one represents, I should say, my equation. My equation, instantaneous rate of change, was 120x minus 1800. And I know that this point, x, is a critical point 15, and I know this one, it can be anything, because we do not, the domain can go anywhere. But nonetheless, we think that x equals C15 is going to be our critical point. What happens now, I try to pick up a number from here to this extent. It can go all the way to minus infinity, and from here it goes all the way to plus infinity. It's not like the previous one that we had to just go from 0 to 37 then. Now, if I just put x equals to 15, how much is going to be my instantaneous rate of change when x is equal to 15? How much is that going to be when you put x equal to 15? 120 times 15 minus 1800. Then how much it becomes? 0, huh? Because we know that that was a root of our equation. That's why at x equal to 15, we know that this equation which we have here, 120x minus 1400, which it itself is the equations for d of px over dx, the instantaneous rate of change, it becomes 0. Okay, now I'm just going to come here from this, I should say, pick up a random points from the left of my critical point. I'm going to pick up, for example, the number which it's going to be, for example, 0, because it's going to be the easy one. I know that the 0 is going to be on the left side of my critical point. Then I come to say, okay, what is going to be the instantaneous rate when x can be 0? You can come with any other number. You can come with x equals to, let's say, 5, 4, 14, anything less than 15. I pick up 0 because 0 is very easy. When I plug it into that equation, the first term, which is 120x, is going to vanish, because you say 0 times 120, then it vanishes that term, then you get only becomes minus 118, which you will see that this number, it's less than 0. Then as a result, we come here and we say that, okay, it's going to be a negative sign based on the sign that we derived from here. Then it means that if you go back to this as in terms of the geometric representation, you see that the slope of the points, anything between, I should say, between, oh, sorry, I just made a mistake. Here, it's not going to be, let's say, minus infinity, because you see that because we have the intercept, which is essentially $1,500, the intercept, we cannot go beyond that, because that's where you see the beauty of doing an interpretation before. Because before that, we cannot have the ticket's price to be minus. Then that's why we had to just do this one. We can just go from x equal to 15 all the way to 1,650. And now it means that as a geometry representation means any points between, I should say, sorry guys, again, I have to make it correct because it has to be 0, sorry. 6 and 15 is for the y-axis, not for this one. It was my mistake, sorry. It's x has to be 0, because you see that when you go beyond the x equal to 0, which is 0 is here, you cannot have the x's, which is negative for a ticket price. Then that's why we just restrict ourselves to this interval. Okay, now you see that it's going to be negative. It means that any line, the tangent of the slope of any tangent line between these points to this point is going to be negative. It means that it's going to be along this direction. But however, after x equals 15 to, let's say, to plus infinity, I'm just going to pick up a number. For example, I'm just going to say, I'm just going to pick up x equals to 20. Then the instantaneous rate of x equal to 20, it becomes what? I plug 20 inside this equation. Then I have 120 times 20 minus 1800, which becomes 600 plus, which is a positive number, which it means that in this interval, from x equal to 15, going all the way to the infinity, if you pick up any number, which we randomly selected to be 20, because it was easy to calculate that, we get the plus number. We get the positive number. Then now it's going to be the crucial thing to learn. The crucial thing to learn, guys, is this. Whenever you have this chart, you identified the variation of the sign of the instantaneous rate of change. We looked at the variation of the sign. Here, we have minus. For example, it's going to be like this. You are here, you have a minus. You are sad. Now you become positive. It means that you are happy. Huh? Now, when you have this sudden change from sad to happy, or from minus to plus, this point, which we talked about, this point, which is x equal to 15, but this sign becomes what? The point of the minimum. You see that these points now, it's the minimum. It's the lowest amount of the profit that you get. You see, the lowest amount is just 3,000. Then we say that the XC, the critical point, is essentially the X minimum or X min. MIN stands for the minimum. That's going to be the lowest amount. Then also you see that any points which the slope of instantaneous rate of change, the slope of the tangent line is negative, then suddenly it becomes positive, then that point would represent the minimum. And these things that we covered so far, the maximum or the minimum, or let's say, for example, these kind of stuff, there is a very important name we assign to them. We call them local minima for this case, and for the other case, which it was the maximum, we call them local maxima. We talk about the locality in a one specific form. We talk about the global maxima and minima in future lessons then. Okay. And also, we can come here on the previous slide. You see that on this one, you are happy now here, you have a positive sign. For example, you have positive here. You say that here you have happy, but here you become sad. You become sad. Then from happy to sad, it's, I should say, the maximum. Okay, that's what we talked about this one, and essentially that's all the lessons that we had to learn today. Any questions, guys?
No.
Any questions?
No.
No.
Lara, any questions?
No.
Sylvia, any questions?
No question.
Thank you. Jasper, any questions?
No.
Nope.
Anki, any questions?
No.
No, everyone is fine. Guys, remember, the things that you learned today, you have no idea the significance of it. This is the thing that which they call that, I should say, you talk about that when you just want to go to the concepts that this is called optimization. The things which you learned today, you talk about that also in the calculus class, and when you go to the engineering or business, you talk about this stuff as the method for optimization. Either you optimize your model or optimize your algorithm. We're going to talk about lots of this stuff, more advanced of this stuff when we go to our mathematics lab. In the lab section, we talk about the functions and algorithms that optimizes. It means that either it brings them, it minimizes, for example, the errors, or maximizes the output. We are going to talk about this one in reality very much in future, but this one is the fundamental that we had to learn. I hope that you learn it perfectly. Then it's now going to be the time, it's 10:55. We are going to take 15 minutes break. That's going to be our second break. We come back by 11:10. Then when we come back, we do more exercises, but it's going to be your turn to just do the exercises. Okay? Any questions, guys?
No.
No? If no questions, guys, enjoy your break. Come back by 11:10. By 11:10, when you are back, we move on with some cool stuff then. Okay?
Okay.
See you guys in 11:10. Bye for now. Okay, let me share that screen. If everyone is fine and no question, then we have an exercise to do now in order to consolidate the things that we have learned. And then as a result, the things that you want to do is going to be this. I just want to ask everyone, please, to go to the textbooks which we have. And please go to page number, I should say the page number, as you can see, is 113, chapter 2. When you just go there, please go to exercise number 12. Exercise number 12. That you will see that we have done a basic mathematical modeling, which is going to be this. Rx, which is essentially, you see that it talks about the weekly revenue for battery cells at store. And Rx represents the revenue. Revenue means the sales, the amount of the sales that they just make in dollars, for example. And you see that. And the X, Rx represents the function, which represents the revenue, which that store generates. And X represents the cost of the package of the batteries then. You see? The cost of the package of the battery, X. And all of the things are in dollar. Or the total revenue is in dollar. The X, the cost of package of batteries, is going to be also in dollar. Guys, I just want you, please, because you have to write, as you will see here, it says that you have to write a detailed instruction. I want you, please, follow that question number 12. Do that. I think 10 minutes, half an hour is going to be fine. Write a detailed instructions, exactly as what I did that for you. I had to plot it, find the intercepts, and find the interpretation of the intercepts. Then I followed those steps, and at each step I had to make an interpretation of the things which I did. Please, you do the same thing for question number 12 on a neat piece of paper. By 11:45, please email it to me before we end the class. Email it to me on the Schoology then. Okay, please remember, make it detailed instructions as what I have done for you. Do not just put the equation and that should be done there. Detailed instructions. Okay, please start doing that. It's now 11:14. Please, by 11:45, which is almost 31 minutes, half an hour, email it to me on the Schoology then. Very neat and detailed. Okay, does it make sense to everyone?
Yes.
Yes.
It's page number 113 of the textbook. Okay, everyone is fine. Anybody has a question now? And remember, the last part, which is said that exchange instructions with a partner, it's you do that individually. You do not work that in a group then. And I'm here in case if you have any questions, please ask me. I answer you that. Okay.
Okay.
Great. Okay, let me now. I'm just gonna stop sharing the page. Everyone has that book open for yourself?
Yes.
Okay. If so, let me stop sharing. Let me go to share the screen with the whiteboard. Save the thing, which we did. Okay, good luck, guys. And remember, for tomorrow, we are just going to start with either the R or R Studio. We are going to run our first mathematical modeling using the R. And tomorrow, that's going to be the plan. And I'm here to ask me any questions in case if you have.